Chapter number 5, Exploiting Memory Hierarchy. In the previous chapter about the Central Processing Unit CPU, where we discussed about the Arithmetic and Logic Unit ALU and the Control Path Implementation, we also looked at different techniques for improving the performance of processors. This chapter discusses about another component of the digital computer called memory. Whenever we look at the memory system, we would want to have fast, large, and also cheap memories. Now, having all that together is not possible. Faster memories are more expensive and may also occupy more space. Therefore, having all these features together in a memory system is not practical, and the only solution to reap all the benefits is to have a hierarchical memory system. Principle of locality. In a hierarchical memory system, the entire addressable memory space is available in the largest, slowest memory, and incrementally small and faster memories, each containing a subset of memory below it. Process proceed in step up towards the processor. This hierarchical organization of memory works primarily because of the principle of locality. That is, the program accesses a relatively small portion of the address space at any instant of time. We are aware of the statement that the processor spends 90% of time on 10% of the code. There are basically two different types of locality, that is temporal and spatial. Number one, temporal locality means if an atom is referenced, it will tend to be referenced again soon. For example, instructions in a loop, induction variables, etc. And second type is spatial locality. If an atom is referenced, atoms whose address are close by tend to be referenced soon. And for the past 2 decades or so, the hardware has relied on the principle of locality for providing speed. Examples of spatial locality is sequential instruction access, array datas, etc. We take advantage of principle of locality by implementing the memory of computer as memory hierarchy. A memory hierarchy consists of multiple levels of memory with different speeds and sizes. The faster memories are more expensive per bit than the slower memories and thus are smaller. The faster, smaller, and more expensive memories are closer to the processor. As we move away from the processor, the speed decreases, cost decreases, and the size increases. The registers and cache memories are closer to the processor, satisfying the speed requirement of the processor. The main memory comes next and last of all. The secondary storage which satisfy the capacity requirements. A memory hierarchy can consist of multiple levels, but data are copied between only two adjacent levels at a time, so we can focus our attention on just two levels, the upper level and the lower level. The upper level, the one closer to the processor, is smaller and faster than the lower level since the upper level uses technology that is more expensive. Figure shows that the minimum unit of information that can be either present or not present in the two-level hierarchy is called a block or a line. A hit is set to occur if data appears in some block in the upper level. Hit rate Hit rate is the fraction of memory accessed found in the upper level, and hit time is the time to access the upper level, which consists of RAM access time plus time to determine hit or miss. A miss is said to occur if data needs to be retrieved from a block in the low level. On the other hand, miss rate is equal to 1 minus hit rate. Miss plenty is the time to replace a block in the upper level plus time to deliver the block to the processor. Hit time is normally less than miss plenty. When a word is not found in the cache, a miss occurs. Different type of memories. There are different types of memory available. One classification is based on the access speed. A random access memory RAM has the same access time for all locations. There are two types of RAM, dynamic and static RAMs. Dynamic random access memory has high density, consumes less power, is cheap and slow. It is called dynamic because it needs to be refreshed regularly. On the other hand, static RAM or SRAM has low density, consumes high power, is expensive and fast. Here the contents will last forever until power is lost. We also have not so random access technology where the access time varies from location to location and from time to time. Example of this type of memory include disks and CD-ROMs. There is also one more type of memory called sequential access memory where the access time is linear in location, for example magnetic tapes. Normally dynamic RAM or DRAM is used for main memory and static RAM SRAM is used for cache. The speed of the main memory is very low in comparison with the speed of modern processors. For good performance, the processor cannot spend much of its time waiting to access instructions and data in main memory. Hence, it is important to devise a scheme that reduces the time needed to access the necessary information. Since the speed of the main memory unit is limited by electronic and packaging constraints, the solution must be sought in a different architectural arrangements. An efficient solution is to choose a fast cache memory, which essentially makes the main memory appear to the processor to be faster than it really is. So the cache is a smaller, faster memory which stores copies of the data from the most frequently used main memory locations. As long as most memory accesses are to cache memory locations, the average latency of memory accesses will be closer to the cache latency that can the latency of main memory. We look at a very simple cache in which the processor requests are each one word and the blocks are also consist of a single word. Figure shows such a simple cache before and after requesting a data item that is not initially in the cache. Before the request, the cache contains a collection of recent references x1, x2, up to xn minus 1, and the processor request a word xn that is not in the cache. The request result is a miss and the word xn is brought from main memory into the cache. In looking at the scenario, there are two questions to be answered. Number one, how do we know if a data item is in the cache? And the second question is, if it is there, how do we find it? The answer are related. If each word can go in exactly one place in the cache, then it is straightforward to find the word if it is in the cache. The simplest way to assign a location in the cache for each word in memory is to assign the cache location based on the addresses of the word in memory. There are three different mapping policies: direct mapping, fully associative mapping, and n-way set associative mapping. We discuss here direct mapping. Direct mapping, this is the simplest mapping technique. In this technique, block I of the main memory is mapped on the block J modulo of the cache. Modulo means the number of blocks in cache. If the number of entries in the cache is a power of 2, then modulo can be computed simply by using the lower order log 2 into cache size in blocks. Bits of the addresses. Thus, an 8 block cache uses the 3 lowest bits. 8 is equal to 23 of the block addresses. 8 is equal to 2 to the power 3 of the block addresses. For example, in the figure shows how the memory addresses between items 0001 of 2 of binary and 29th mean 11101 map to the location items 001 and fifth location 101 in a direct mapping cache of 8 words. How do we know whether a request word is in the cache or not? We answer this question by adding a set of tags to the cache. The tags contain the address information required to identify whether a word in the cache corresponds to the request word. The tag needs just to contain the upper portion of the addresses corresponding to the bits that are not used as an index into the cache. For example, in previous figure, we need only have the upper 2 of the 5 addresses bits in the tag, since the lower 3 bits index field of the address selects the block. Architects omit the index bits because they are redundant, since by definition the index field of any address of a cache block must be that block number. As a main memory address is generated, first of all, check the block field that will point to the block that you have to check for. Now check the tag field. If they match, the block is available in cache and it is a hit, otherwise it is a miss. Then the block containing the request word must first be read from the main memory and located into the cache. Once the block is identified, use the word field to fetch one of the 64 words. One more control bit called the valid bit must be provided for each block. This bit indicates whether the block contains valid data. The valid bits are all set to 0 when power is initially applied to the system or when the main memory is loaded with new programs and data from the disk. Transfers from the disk to the main memory are carried out by a DMA mechanism. Normally, they bypass the cache for both cost and performance reasons. The valid bit of a particular cache block is set to 1 the first time this block is loaded from the main memory. Whenever a main memory block is updated by a source that bypasses the cache, a check is made to determine whether the block being loaded is currently in the cache. if its valid bit is clear to 0. This ensures that the stale data will not cache exist in the cache. Cache example. The cache contents are shown after each reference request that misses, with the index and tag fields shown in binary of the sequence of addresses. The cache is initially empty with all valid bits. V entry in cache turns off mean n. The processor requests the following address, that is 22. Now we convert 22 into binary and its binary is 0, 1, 1, 0, 1. The first 3 bits are used for the indexed in the cache, and the last 2 bits 0, 1 are used for the tag in the cache. So initially our cache is empty, so 22 word is not in the cache, so it is a miss. Then pro program loads the 22 words from the memory and placed it on the index of 0, 1, 1, and the n bit is now converted from n to y, and the data is 10110 is now present in the cache. If we want to see another word, for example 26, first of all we convert this word into binary 01011. 010 is these 3 bits are used for the index of the cache. Initially our cache is empty, so the index 010 is empty, so that's why it is a miss. And now we update, now computer updates this index with 26 value, and tag is given, and the last 2 bits 1, 1 are used for the tagging of this memory location. Similarly, if system needs to find 22 and 26 word into the memory, first of all we convert 22, that is 01101. Compiler check 011 indexed whether value is present or not. This time we already store a 22 value in the cache, so this time this is not a miss, it is a hit, and a tag 01 is placed, and compiler cache is a hit. Similarly, another word 26. Already we store our 26 word into the memory, so it is again hit, and 010 index is filled with our 26. Now uh, if a system or processor wants 3 words 16, 3 and 16 looking into the cache, first word 16 we convert it into its binary, that is 00001, and this is a miss because 000 index is initially empty. So first of all we tag this index with 01 bit, that is the last 2 bits of the 16, and the data is updated, that is 00001. Second word 3, that is 11000. First of all check the index 110 whether value is present or not. This time value is not present, so this is a miss, and this index point is updated with the data 1100 and the tag 00 is placed in the tag field, and the last one, 16, we already filled the index 000 with the 16, so this time is a hit, and uh, no need to update the tag. Another example is computer wants the word 18, looking a word 18 into the memory, and so here is the answer that the figure shows the cache contents after each bit in the sequence has been handled when address 18 mean 010001 is referenced. The entry of address 01011 26 must be replaced, and a reference to 01011 will cause a subsequent miss. The tag field will contain only the upper portion of the address. The full address of a word contained in cache block I with the tag field j for this cache is j multiplied by 8 plus 1, or equivalent the concatenation of the tag field j and the index field I. For example, in cache F above, index 010 has tag 01 and corresponding to the address 01001 in a binary. Figure for the cache shows the lower portion of the address is used to select a cache entry consisting of a data word and a tag. This cache holds 1024 words or 4 kilobyte memory. Unless noted otherwise, we assume 64-bit address in this chapter. The tag from the cache is compared against the upper portion of the address to determine whether the entry in the cache corresponds to the request address. Because the cache has 012 mean 1024 words and a block size of one word is equal to 10 bits are used to index the cache, leaving 64 minus 10 minus 2 is equal to 52 bits to be compared against the tag. If the tag and upper 52 bits of the address are equal and the valid bit is on, then the request hit in the cache and the world is supplied to the processor. Otherwise, a miss occurs. Here we have another example. In this example, consider a cache with 64 blocks and a block size of 16 bytes. So the question is, to what block number does byte address 1200 maps? The solution is, we already see the formula. The block is given by block address modulo number of blocks in the cache. So where the address of the block is byte address divided by bytes per block, notice that this block address is the block containing all addresses between byte address divided by bytes per block multiplied by bytes per blocks, and byte address divided by bytes per block multiplied by bytes per block plus byte per block minus 1. So with 16 bytes per block, byte address 1200 is blocked address. Mean 1200 divided by 16 is equal to 75, which maps to cache block number 75 modulo 64 is equal to 11. In fact, this block maps all addresses between 1200 and 1215. Increasing the block size usually decrease the miss rate. The miss rate may go up eventually if the block size becomes a significant fraction of the cache size, because the number of blocks that can be held in the cache will become small and there will be a great deal of competition for those blocks. As a result, a block will be bumped out of the cache before many of its words are accessed. Stated alternatively, spatially locality among the words in a block decreases with the very large block. Consequently, the benefits to the miss rate becomes smaller. A more serious problem associated with just increasing the block size is that the cost of a miss rises. The miss plenty is determined by the time required to fetch the block from the next lower level of the hierarchy and loaded it into the cache. The time to fetch the block has two parts: the latency to the first word and the transfer time for the rest of the block.